This is a fractal pattern, and this is only one of the many applications of a concept called recursion. Found mostly in mathematics and computer science, this is a topic that's notoriously hard to understand when you first learn about it. In this video, we'll try to shed some light over recursion as seen in computer science. But instead of just jumping right into its definition, we'll start by briefly looking at two very important topics: the stack and function execution. Only after we've laid down this foundation will we look at what recursion is. And I advise you to not skip the first two parts because, in my opinion, the main reason why people struggle with recursion is a lack of knowledge of these two topics. So, let's begin with the notion of stacks. In computer science, a stack is a linear data structure that can be accessed at only one of its ends. So, if we take as an example this collection of rectangles we see here, we can say that this is a stack if we add and remove elements from only one extremity. If we decide to use the left side, like we do here, we need to do all the adding and removing from there and make sure we never use the other end. It's also not allowed to add to or remove the ones that are in the middle. Similarly, if we decide to use the right side, we need to always stick with it. Because of this rule, stacks are a last-in, first-out structure. Whenever we want to remove an element, it will always be the last one that was added. Stacks are sometimes pictured vertically, with the newest added element being at the top. You can imagine it as if you were looking down from above the stack and the only block you can see and do anything about is the top one. If that's gone, the one underneath it will be the new top, and so on. The two actions of adding and removing from a stack have their own names. We say we push items onto the stack when we add them, and when we remove them, we pop them off. And that's pretty much all you need to know about stacks to understand recursion. Let's now move on to the second topic of this video. So, what happens under the hood when we call a function? Calling a function, also known as invoking it, is done in most languages by writing its name followed by any potential arguments inside a set of parentheses. When our computer interprets code like this, it recognizes that we invoked a function and it does a really important thing. It creates a private, enclosed space which stores some information about this current execution. This pool of information is usually called a stack frame, an execution frame, or an activation record. The specific implementation details might differ from language to language, but the general idea is the same. Inside this frame, we'll have a couple of things stored regarding our function. The most relevant for us right now are local variables and arguments. A link to the previous execution frame. We'll see in a minute what this means. A reference to the last instruction. This is to be able to resume the execution when a new function is called. And a return value. This entire frame will be placed on a stack structure like the one we saw at the beginning of this video, called the call stack. All of this doesn't really mean anything without an example, so let's go ahead and have a look at some simple code. So we have here three function definitions. Green, which defines a variable named color and sets it equal to the string green, and then prints the word cyan. Red, which defines another variable called color, it prints the word crimson and then invokes the green function. And finally, we have blue, which invokes the red function and then prints aqua. Let's now see what happens when we invoke blue. When we run this Python file, our computer will start using a call stack with the module frame at the bottom. Depending on where you run your code from, this frame can have a different name, but don't get too hung up on it. It just contains some general information needed for the current execution. I'm just showing it here in case you decide to inspect the code yourself and you run into it. Okay, so at line 23, our computer recognizes that this is a function call, and it will create a stack frame for the blue function. Inside it, it will store all the information we just talked about. Local variables and arguments. In this case, we don't have any since we didn't define any variables, and blue doesn't take any arguments. A pointer to the caller's frame. This is a link to the frame that initiated the call to this function. We can think of this one as asking the question, who called me? In this case, it's the module frame. Our last instruction reference, we'll see in a minute when this is useful. And we also said we have a return value. Blue doesn't return any particular value, so the implicit none will be returned instead. Since this is the case for all our functions, to save us some space, I'm not going to show it here, but just remember that all functions return some value, and in our cases, it's none. And after all of this is set up, all the lines inside blue will be executed one by one from top to bottom. The first one is 19, which, as we can see, is an invocation of the red function. At this point, something very important happens. The current execution of blue is temporarily halted, and the code from line 19 is saved as the last instruction that was run inside this frame. And because we have a new invocation, a new stack frame is created which will contain the details of red, a local variable named color, a link to the caller's frame, which in this case is blue, and the last instruction. And now the execution moves inside red. We have a variable assignment at line 13, which we already mentioned, and then at line 14 we have a print function call. At this point, the execution is again halted, the last instruction value is saved, and a new frame is created on top of the red one. Its code will run, printing the word crimson to the terminal, and after it finishes, it will be removed from the stack, giving the control back to the caller. And because we saved the last instruction that was run inside this frame, we know exactly where to resume the execution, which is at line 15. And that is again a function call. The last instruction inside red will be updated, and a new frame is created for green and placed on top. The execution is temporarily halted for the red function, and we move inside the green one. There, we have a variable initialized at line 8, and at line 9 we have another print function call. And once again, the new stack frame will be created and placed on top. After it's done printing the color, it will be removed from the stack, and the control is given back to the caller. So now we're back in the green function, but we can see that there's nothing left to do here. 9 was the last line inside green. So the frame will just be removed from the stack and we continue the execution inside red. Notice the last in, first out pattern that the call stack is enforcing. The last function that was invoked will be the one at the top, actively executing its code. And after it finishes, it will be the first one to be removed. Inside the red function, there are also no more lines to run, so we go back to its caller, which was blue. We read line 20 and yet again another print function call. It will follow the same rules as all the other ones, and after it finishes, it will be removed from the stack and blue will take over again. With no more lines inside it, its frame will also be removed from the call stack, and the control is given back to the module frame at line 24. Here, it will proceed to the next lines, calling any other potential functions remaining in the file. And this is how function calls are orchestrated using stacks, and it's how our computers run the code that we write. Take a moment to really understand these concepts. Replay this part of the video if you need to. They're not only important in understanding recursion, but also give us a window into how our code is being executed behind the scenes. If you want to dive deeper into these topics, you can have a look at the inspect or the traceback modules in Python. And if you're really feeling adventurous, you can even analyze the C implementation of the stack frames in the Python source code. I'll leave links to all of these in the description down below. But I think that regardless of the implementation details of different programming languages, we can summarize the process like this. Function execution is managed with a stack structure named the call stack, and each new invocation creates its own stack frame with its private pool of information and is placed on the call stack. When a new function is called, the current running one is temporarily halted, and a frame for the new one is created and placed on top. When the function at the top finishes its execution, it will be removed from the stack and the previous one will resume where it left off. So, now that we know how function execution works under the hood, we can finally tackle the concept of recursion. Recursion is a method of solving a problem where the solution is defined in terms of a smaller version of itself. In computer science, that's done when a function calls itself from within its own code. Now, if this is the first time you're hearing about recursion, these two definitions will probably not make too much sense. So I suggest we step away from the definitions for now and look at a well-known recursive example and build our understanding from there. And the example we're going to analyze is the notion of factorial. In mathematics, the factorial of an integer n is the product of all positive integers less than or equal to n. So what does that mean more precisely? Let's take the number 4 as an example. 4 factorial, which is written as 4 followed by an exclamation point, is equal to 4 times 3 times 2 times 1, and we stop at 1 since factorials only work with positive integers. 3 factorial would be 3 times 2 times 1, 2 factorial is 2 times 1, and 1 factorial is just 1. 0 factorial is by definition 1. There's no multiplication here, it's just a mathematical convention. No negative values are allowed, so we stop here. Now, if we were to take a closer look at these numbers, we can see that we have 3 times 2 times 1 as part of 4 factorial's definition. But just one line underneath, we see that the same operation is in fact 3 factorial. So this means that we can replace this part in 4 factorial's definition with 3 factorial. And now we have 4 factorial equal to 4 times 3 factorial. This is what the definition from a minute ago meant. We solve 4 factorial by first solving a smaller instance of the same operation. And of course, this pattern is repeated on all the other numbers. So, seeing all of this, we can generalize that for any number n factorial is n times n minus 1 factorial. Alright, so let's try to write that in Python code. Factorial as a function is not too complicated. We take a positive integer n as a parameter. We need to make sure we include the scenario where n is 0, in which case we return 1. And finally, we return n times factorial of n minus 1. And this last bit is important. For this function to be recursive, we have to invoke it inside its own definition. So this factorial is the same as this one. It's not some external function we defined somewhere else. This is what we meant when we said that recursion is when a function is calling itself. So how can this even work? Let's have a look. Let's see what happens when we invoke factorial with 4 as an argument. As we just learned, a frame will be created for this function call and placed on the call stack. The lines of code inside it will then start executing. The first one is to check if n is equal to 0. With n being 4, this condition is not met, so it will move to the next line, where we have the return statement and a new invocation to factorial, this time with n minus 1 as the argument. Since we now have another function call, the execution for the current frame stops, and a new one is created for factorial 3. Here we start executing the code from the beginning, this time with n being 3. We end up at the line where we have another function call for factorial 2, and again, a new stack frame is placed on top of the running one. We follow the code again, and we end up with factorial 1. And lastly, we're calling factorial one more time with n equal to 0. The first line inside our function will check if n is 0, and this time it finally is, so the return line inside the if clause will run. Now, remember when I said that each function has to return a value? Well, this is where we use that information. Since we hit the return keyword, the execution ends, and the return value of 1 will be passed down to the below frame, at the same line where the invocation happened. Now, you might be inclined to believe that we won't have anything to do inside that frame, since that was the last line, but that's not the case. Because, you see, one line of code we write in our programming languages may contain many lines of low-level machine code. This means that this return 1 times factorial of 1 minus 1 is actually composed of multiple instructions. In our case, we have the function call, the multiplication, and the value return. And when the function call takes place, that is the instruction we pause at. And after it's done, we continue with the multiplication, and then we return the value. Okay, so inside factorial 1, we do the multiplication, and then the frame is removed from the stack, and the result is passed down to the caller. From now on, we have a cascading effect, multiplying the value we received from the previous call with the current value of n, until finally the last frame is removed, and we get the result for our initial invocation, which is 24. And that's how recursive functions work. They follow the same rules as any other function. It just so happens that we're calling the same one. But every time we do it, it's within its own private enclosed space. And this is where I think the confusion comes from when first trying to learn about recursion, thinking that the entire process happens inside one function call. That can lead to questioning how factorial can possibly work, since the code inside it relies on the result of factorial itself. Thinking like that would be like trying to imagine you're building a hammer using as a tool the same hammer you're trying to build. It's an unending thought loop. The better way to understand this, in my opinion, is to imagine that function definitions are just a list of instructions that you keep on the side of your desk. And whenever you invoke that function, you take a blank sheet of paper. You check the instructions and you follow them using the arguments for that particular function invocation. When you hit another call, you take a new piece of paper. You put it on top of the previous one, check the instructions, and then repeat the process again and again until you hit the condition to stop. When that happens, you take the result you got from this last invocation and you pass it down to the previous one. You finish what you had to do in this frame, you throw away the paper, and you continue inside the next one, and so on until you get the final result. I think this is a more accurate representation of the whole process. Okay, let's now have a closer look at our factorial function and talk about two key aspects. The first one is this bit of code over here. This is called the base case, or the ground case. It essentially tells us when the recursion should stop. We know that by definition, factorials should only work for positive integers, so by putting this condition here, we ensure that our recursive calls stop when it wouldn't make sense to continue. Having a base case is not optional, it's mandatory. Every recursive function must have a base case. What that is, in terms of logic, depends on the problem we're trying to solve. In our example, we stop when we reach 0 because that's the definition of factorial. But if we were to have a recursive function that works with a list, for instance, the base case could be the list to become either empty or one element long. The second thing to notice here is the inner function call. This is called the recursive case. What's important here is the parameter we pass to it. Notice that we're working towards the base case. We decrease n by 1, and eventually we end up hitting the condition we have in the if clause. This is also crucial for having a working recursive function. If we were to go away from the base case, we would never stop. It would be comparable to having an infinite loop. So both these two components, the base case and the recursive case, are essential and have to work together. The base case to define when to stop, and the recursive case to lead to the base case. So this was a simple example, one which basically stems from the definition of factorial. But recursion is also used with more complex data structures, when certain patterns emerge and the problem can be solved by breaking it down into smaller and smaller pieces. Such examples are trees and graph algorithms, or some array sorting methods. But these are topics for another time. I hope that this video provided you with enough information to better understand recursion. Thank you so much for watching, and I hope to see you in the next one.